All right, let's get started. I think we have everyone. Yeah, this should be everyone. So welcome to class 6 of Introduction to Counting and Probability. Hello, Howard. Introduction to Counting and Probability. Today we are going to finish off chapter 5 and talk about distinguishability, as that is what we have not gone to, which is like sort of like the last little like new thing, or like because we've talked about things like when order matters or and stuff like that, like those little like nuances, or like when you have rotational symmetry, right? Like when we have the table, like what does counts as the same, stuff like that. And this is like sort of like another addition to that, where we're gonna talk about whether or not you should consider two things to be look the same and not the same. And again, we've talked about something similar when we talk about letters, right? We were arranging letters in a word, like banana, right? The three A's, we realized that treating them as the same and treating them differently gave us a different number of ways. And we're going to talk about something similar here. And we're gonna learn we're gonna see how important it is that we like sort of understand the difference and how we can understand in our head the best way to do so. We'll probably have a quiz. I should write that down. We'll probably have a quiz on chapter 5. Actually, we will. Actually, I'm going to say we will. We're going to have a quiz on chapter 5 after distinguishability. And after that, we're going to do some harder problems. AKA chapter 6 is basically all problems. And yeah, because at some point, right, like once you learn the counting fundamentals, it's about being able to apply them in interesting ways. That will allow you to solve further problems beyond, right? But the point is, you guys have some good fundamentals now, and we will see how well you guys do with some of these different problems. Again, after class, I'll release homework. I think I saw most of you submit the homework, but when I checked it like 2 hours ago at least. I haven't checked it now. Let's have a look right now. It looks like pretty much everyone submitted it, which is great. Thank you again. I'm very sorry that I graded my chapter 4 really late. Hopefully no one's like too upset that I returned it too late. If anyone's very upset at me, you can be upset at me. I'll try to grade stuff faster. But there's still a lot of stuff I have to do before I get back to campus for school. But are there any initial questions before we begin today? Any at all? No? Okay, then let's talk about distinguishability. So, distinguishability, as I said, is if are things different, okay? And your answer is probably going to be like, well, it depends. And yes, the answer is it does depend, right? If you're considering two A's in the word banana, right? Those are different, or those are the same. Sorry. If we're trying to find arrangements, and so in a question, it won't necessarily use the word distinguishable, right? So we like to. So in mathematics, we call it distinguishability, right? Whether or not you can obviously distinguish them. Of course, not every question is going to use the word distinguishable. And it'll be up to you to figure out in that context, what it means. If it's not clear, they'll try their best to provide it to you. But it'll be mostly up to you to figure out whether they mean things are distinguishable. And of course, we know that it has a difference, right? We learned that, for example, if we have banana, right? If I gave a label to every single letter like this, and then this can be arranged like this in 720 ways, right? This is 6 factorial. But we know that they're treated as the same, then there are the 6 factorial, but then we have to divide it by 6 to get 120 ways, right? And so we see the difference here. This is here the A's are distinguishable, right? Well, because they're like different from each other. And of course, in this case, we're going to say that the A's are indistinguishable. So just some words, how we use the word distinguishable and indistinguishable. But that's just generally the gist. What about the ends? Oh, I forgot the ends. I completely forgot banana has 2 ends. I don't know why I forgot about the ends. Sure, I'll give the ends labels too. Like that. Okay. I completely forgot about the end. I don't know what's wrong with me. Right. And but you can, but you know, sometimes sometimes you might have an instance where the ends are distinguishable and the A's aren't, and you'll be mixing and matching there, and ends. For this example though, they're either both indistinguishable or both not distinguishable. But we get the fundamental difference, like not in a math sense, but at least in a logic sense. Like yes, do we want to treat things differently, right? And so there's a difference between if I say, 3 boys, and then if I say, Bob, David, and I'll put my name in there because I can't think of any other male names right now. Right? There's a certain implication here, right? Like the implication here is that that these boys are indistinguishable because you're kind of grouping them together like this. Whereas listing out their names might mean they're distinguishable. Again, this isn't like a perfect rule, but this is the sort of difference when they're talking about, right? Does that make sense? Again, it'll depend from context to context, but that's just an example of how you might want to see the difference. Yes, I see you have pointed out each individual person. Probably means they're distinguishable. Right? And usually the 3 boys will probably be accompanied by, and 2 girls, and it'll be a really small part of the question. Because if it's the main focus, then well, it could be either. But now that we know, okay, so as long as we understand the definition, we're off to a good start. So right now I'm going to address I'm going to show you, now I'm going to, present just how important it is to know the difference between distinguishability and indistinguishability. And we're going to do that using the classical problem of balls and boxes, okay? Welcome to the world of balls and boxes, okay? So we have 4 balls and 2 boxes. And I'm going to draw my best box. Like that. Look at that beautiful box. That is a masterpiece of a box. And there's 2 of them, of course. All right, so we have 2 boxes, right? And we're thinking, and we're trying to figure out how many ways there are for us to put balls in boxes, okay? How many ways can I put 4 balls in 2 boxes, right? And immediately we should hopefully see that there's a twist, right? And the twist here is that, well, for example, do we necessarily care is the number of balls? For example, if I put 2 balls in one box and 2 balls in the other box, is that the same as putting any 2 in any 2, or is it 2 and 2, 3 and 1, 4 and 0? Are those the differences, or is it more like this specific ball, is put in this specific box is different than that other ball being put in that other box? Right? And so here we have a question of 2 distinguishabilities, right? That matter in this question. Are the balls distinguishable? All right, I'll start writing dist from now on because I cannot be bothered to write the word distinguishable all the time. And of course, are the boxes distinguishable? These are the 2 fundamental questions that greatly impact how we're going to look at this question. Because the answer is different, first of all, depending on the answers, right? And so we sort of see that there are 4 different cases we have to deal with, right? And I'll draw a nice little helpful chart to illustrate this, right? Oh, I messed up again. What am I doing? I keep thinking it's 2, 3s. 1, 2, 1, 2, right? And so here, draw a line here. I should not have drawn that much lineage. All right, and there's a difference between what are the boxes and the balls, right? And so the question is, are the balls distinguishable or indistinguishable, and are they indistinguishable, which I'll represent as D and ID. And so let's look at this a little closer. And I'll split it into. It looks like we're having a quiz. It's about to look like we're having a quiz. We are not having a quiz. Do not worry. We're splitting up into these 4 different cases, right? In each one of these 4 different cases is approached differently, right? So our first case is going to be they're both distinguishable. So so the best way to state that distinguishable is to indicate that they're different somehow, usually by giving them names. So we're gonna call, right, and this is going to be the distinguishable case. This is going to be the balls are distinguishable, but the boxes aren't. This is going to be, oh, what the hell is that on my face? And then this is going to be, this is inconsistent. I'm going to not do that. This. And so you see, and so hopefully you guys see that there's I hope you guys see the 4 different cases where you have to address that are going to give us different answers. So the first case is if all 4 balls are different and the 2 boxes are also different or distinguishable, how many ways did it put it in or put the balls in? And the answer, does anyone want to think of how you might do this question? How many ways can we put the 4 distinguishable balls into 2 distinguishable boxes? Does anyone have any ideas? And then remember, so it's just 2 and 2. No, you can put the 4 balls in, like, it doesn't matter. One box can be empty. They can be split 2 and 2. They can be split 3 and 1. The point is that as long as each ball is in a box, then you're good. What if you ate a ball in accident? We'll add a case for you, Howard. Every answer is going to increase by 1. Howard just eats a ball. Charles says you can have 1 and 3 and 2 and 4 and 0. Yes, in terms of number of balls put in the boxes, that is true. But of course, these balls are different, right? What we're saying here is that if I put for example, if I put A and B, and C and D here, it's different from putting A and C and B and D here, which is also different from putting B and D here and A and C here. Do we see that? We see why these are different, right? Due to the distinguishability of the 2 boxes, all 3 of these are different. So does anyone have any ideas as to how we can talk about if all 4 balls are distinguishable and both boxes are distinguishable? How can we figure out how many there are? All right, where's that? And usually this is not something you don't know how to do. I'm not asking something you don't know how to do. I just want you guys thinking about this distinguishable thing, like, oh, like this is different from this, etc. Maybe you focus on one box. I like that, right? So if you focus on one box, then you know what the contents of the other box is, right? Because exactly, that's a great suggestion. So how do we figure out which, so if we're focusing on one box, we can either choose to put in a box or not put in a box, right? Or not, not put in box 1, I guess. So how many choices do we? 4 choose 0. Oh, okay. 4 choose 1. 4 choose 2. Are you adding these all up? Is that what you're doing? Are you like listing them all? What's going on? Okay, well, how about I propose this? Instead of thinking about, it does have a little to do with that, but it turned out to be much simpler than you guys are breaking it. Basically, it works like this. Ball A has 2 choices. It either goes in box 1 or box 2. Ball B also has 2 choices. Ball C also has 2 choices. And incredibly, ball D also has 2 choices. Hence, these are all independent of each other, hence making the answer 16. That is the answer. And again, the reason we're able to do this is because choosing which box it goes into matters, right? The one choice of you're putting a ball in a different box, right? Every ball being put in a different box matters and creates a separate situation, only because these 2 are distinguishable. So, and you'll see the difference more clearly once we do the other 3 cases. But for now, do we agree? Do we see why this answer is 16? Right? Right. Every ball has two choices. Either goes in box 1 or box 2. Cool. If we're all okay with that, then let's move on to the distinguishable, indistinguishable version, which means that this time the balls are still distinguishable, but this time the boxes aren't. It basically means, which hopefully you guys understand what that means. And I won't spoil it because if I tell you what it means, then you guys will figure out the answer. So in this case, how many ways can we do it? Thinking about, okay, this time the ball, the 4 balls are still different. So it matters if I put, A here, it would be different from putting B there. But there is a key difference, which is that the 2 boxes are now indistinguishable. So how many ways can we do that? Does anyone have any ideas? Howard says 8. Why do you say 8? Yeah, that's right. So the answer is 16 over 2 is 8. Why? Because the 2 to the 4 from earlier was number of ways here. But this time, right, this time the boxes groups are different, essentially meaning that if I put, for example, A and then B, C, D here, it is now, these 2 cases are now the same, right? These 2 cases are the same. Do we see why these 2 cases are the same now? As opposed to in the distinguishable case, they were different. Because before it was A is in box 1 and B, C, and D are in box 2, which would have been different from A is in box 2 and B, C, D is in box 1. In this question, it's A is in a box by itself and B, C, D are together in the other box. And by flipping the order, it's still the same thing where you still have A in its own box and B, C, D in the other box. And so do we see why these 2 are different? Because if we do see why these are different, then it becomes immediately obvious that this is just an overcount by 2, right? You can do this for every single thing, right? Every single arrangement, you just flip it around, and that's an overcount by 2. So we just do 2 to the 4 over 2 is 8. Does that make sense? Yes, sir. Okay. Again, it's going to get, and that the 4 different cases here are very important. And the whole point is to get you guys to remember that it matters. Like it really matters that you know distinguishability. All right, cool. All right, let's now do the distinguishable case, which this means that this time, right, the balls themselves don't matter, but the boxes are still different. The boxes themselves are different this time, which means it's less of which balls per se. It's less of which balls, and it's more of how many, right? Because it doesn't matter if I put this like it doesn't matter if I put this first one versus the second one. I'm putting 1 ball in one of the boxes. So maybe think of this more as like a numbers thing now. That's your guys' hint. Knowing that, does anyone have any ideas how we can count the number of ways to put 4 indistinguishable balls into 2 distinguishable boxes? Eight? Why do you say 8? Since there is 2 distinguishable boxes, yes, there are indeed 2 distinguishable boxes. It can be 4, 0, okay, or 0, 4, okay, and so on. And how many of those are there? 8 in total. I do not see 8. I'm sorry. I don't know where you're getting 8. I see your logic makes sense to me, where you're thinking of his numbers as, oh, I'm putting 4 in here and 0 in here, but I don't know how you're counting 8 of them. right? Try to list them all out. Just list them all out, because if it's like 8-ish, just listing them all out is going to work, and you're going to see it is obviously not 8. It's not 6 either. I think you should list them all out. It's 5. The answer is 5. There are only 5 of them. The answer is, Aaron, I have no idea you got 8. I'm going to be honest. Like, but yes, the way Aaron did it is correct. Instead of thinking of the balls differently, the balls are the same. So it's just the number of balls that matters. So I give him a 4 in. Let's just say if I write in this notation, it means box 1 and box 2. Basically, I can distribute the balls in this many ways. I can distribute the balls. I gotta put all of them in box 1. I put 3 of them in box 1, 2 in box 1, 1 in box 1, or none of them in box 1, and put the rest in box 2, regardless. And this, of course, yields 5 answers. Cool. But does that make sense? And again, we see why we're able to do this in this question, because the balls are different this time, right? In this case, there is only one way to put 4 balls. There's only one way, for example, to put 3 balls in box 1 and 1 ball in box 2, because all the balls are the same, right? I'm just saying, unlike before, where it would have been different to put A, B, C versus A, B, and D. But that doesn't matter here anymore. It's just the fact that, I'm putting 3 and 1. So hopefully that makes sense to people. And the final bit, of course, is when they're both indistinguishable. So how many ways do I have to put 2 indistinguishable balls into 2 indistinguishable boxes? And hopefully the last question should have inspired you as to how we can think about this question. 2.5, an excellent deduction. I see you've divided 5 by 2. Unfortunately, that probably isn't right, because it's a non-integer number. And unfortunately, non-integer numbers there's not really 2.5 ways to do anything. So I'm gonna have to ask you to rethink that, Howard. 3, and why do you say 3? You meant 2 for the second one. Yes, you did. 4 is here. So Howard says we can list it again, and if he starts listing it, right, we get to here, and he just stops, and he says the answer is 3. Yes, but that's the thing, right? 1 and 3 is the same. In this case, it's different. 1 and 3 is the same, because it doesn't matter. The point is, 1 box is 3, 1 box is 1. It doesn't matter which box is which. 1 box is 3, 1 box is 1. And which is why it's 2.5, because this 2 case, right, isn't like halved, right? Before, in the distinguishable case, we just did, like the 2 only appeared once, and it's not like a repeat 2, you know. So that's why the division by 2 isn't exactly perfect. But yes, 1-3 is the same as 3-1 in this case. Simply because it doesn't matter. Because again, it doesn't matter. You know, I put 1 ball in this box and 3 balls in the other box. It's the same. Basically, if I rearrange the 2 things, if it's the same, then it's distinguishable. Oh, if it's the same, then in indistinguishable cases, it's the same concept. But hopefully we see the difference, right? And hopefully we see the importance of understanding distinguishability in problems, right? And you see they always produce different. You usually produce different answers. Of course, you might get problems that do have the same answer if you treat them the other way. But yes, there's a very classic example of distinguishability in full force. And hopefully you guys understand all 4 of these cases. And again, it's not about, like, there's obviously like formulas, right? But it's more important to understand why these come about. Like why in the double distinguishable case we're able to say 2 times 2 times 2 times 2, 16, done. Why couldn't we have said that for the one below it, you know? And that's like the more important thing to understand here. But hopefully that makes sense to people. I highly recommend taking a screenshot of this, by the way, as this is like an extremely important slide. So if you guys want to take a screenshot for your own viewing purposes, you guys can use it during like the P-set and the quiz today if you would so desire. Because I just want you guys to get this down, the difference and how we think about the problems differently, and not necessarily remembering the formula. Try to understand why we're listing out for the indistinguishable ball cases, but for the above ones we were just using 2 times 2 times 2 times 2. Cool. if that is the case, then let us do some problems. So we have how many? I think we have 8 people here. Oh my god, that means everyone gets a question. No way, this is gonna be insane. All right, so here's what we're gonna do. Because I want to make sure everyone does this, we're gonna do 5.4.1, and you'll notice there are 4 parts to this question. But we're also gonna do 5.4.3, and of course, there are 4 questions. So which means that we're gonna do. So basically, I want you guys to do basically what we did, but for 2 other cases. So our examples did it for 4 balls and 2 boxes. So 5.4.1 does it for 5 balls and 2 boxes, and 5.4.3 does it for 2 balls and the general n boxes for n greater than 2. I will not allow anyone to call dibs on anything because some of the problems are significantly easier than others. And I expect everyone to try all the problems. And because of that, I will give you guys a nice, healthy 20 minutes to try these problems out. No, I will not assign them now. If you guys need more time, I want you guys to get all these problems. Hopefully 10 minutes per is like reasonable. But yes, try these questions out and refer back to the slide if you so need it. But again, try not to memorize. Try to understand why it works. Don't just be like, oh, you know, I'm just gonna use the formula, you know, or just like, haha, general fall. But as long as you guys get the theory behind it, then you guys don't need to memorize anything. All right, good luck. All right, it's 4:48. Let's talk about these problems. Again, there are 8 of you, so I've assigned a problem to each one of you. So yeah, everyone gets to participate this time around. Fantastic. So let's talk about some problems. Starting off with 5.4.1, we have 5 balls and 2 boxes. So let's go in order. Part A, both distinguishable. Myron. Oh, here's the thing. Yeah, here's the list again. You guys might want it. Just know you. So yeah, you guys got your type. You guys go and type some stuff. Yeah. So Myron, 5.4.1 AE. Howard, I don't know why you're Howard. I don't know. Yeah, you're typing your stuff already. Yeah, I accidentally hit enter, unfortunately. Well, Howard's ready. I'm glad Howard is ready to present his solution. Fantastic. Myron, are you there? I haven't heard anything in the chat from him. Oh yes, he's here. Okay. 5.4. Oh, he's typing. Okay.
Sorry, I just got back. Which question are we on?
Oh, we haven't. We haven't. I'm waiting for mine to type. I just put up the list here.
Okay.
Yeah. Right. So Myron says for this question that that 2 to the 5 is the answer. I think I accidentally did that inside. Yes, every ball has 2 boxes to go to, right? So this is the double distinguishable case. So if we look back to our old example here, you notice that we use the 2 choices thing, which is because they're both distinguishable, every choice was independent of each other, and you wouldn't have any repeats. So just the answer is just 2 times 2 times 2 times 2 is 32. Good. Part B, Rin. I know you just got back.
Yeah. Basically, so the way I solved it was just I divided the part A answer by 2, so 32 divided by 2 is 16. Since basically since they were distinguishable, it was basically counted twice in the indistinguishable case.
Right. So because the boxes are no longer distinguishable, having basically every case is counted twice, where you have either stuff in box 1, like some stuff in box 1, other stuff in box 2, and you flip it around where you have that other stuff in box 1 and that stuff in box 2. So just overcounting by factor of 2, divided by 2, perfect. Part C, Ling. Because the ball is not distinguishable, we simply need to count the number of balls in distinct boxes can be paired 6 ways, so the answer is 6. That is fine. I know what you mean. Basically, because the balls are no longer distinguishable, only the number of balls that are in each box matters. And if you list them all out, or you just count them, in whatever way you feel right, you can distribute the 5 indistinguishable boxes, into 2 distinguishable boxes in these 6 ways. Correct. And part D, Howard. Oh, Howard's already got his stuff here. That's right. Right. And so if you look at the stuff we have above, it turns out that 5, 0, and 0, 5 are the same. 4, 1, and 1, 4 are the same, and 3, 2, and 2, 3 are the same. In the case of the boxes being indistinguishable, hence this only gives you 3 as your answer. Cool. All right. Good work, everyone. 5.1.3. In this case, right, we're now working with a more general n, which is exciting. So, let's get to it. 5.4.3a. Rocky. Turn my light. There are n options for each of the 2 balls, so there's n times n or n squared, correct? Right, every ball has n boxes it can go into, and they are independent of each other, and they each could produce a different solution because they're both distinguishable, right? So that's correct. Awesome. Part B. How many, if the balls are distinguishable and the boxes are not? And I'm looking for Nancy. The balls are distinguishable, but the boxes are not. Two. Yes, correct. Why is it 2? I mean, you can give me the 2 cases if you want. Like, you can be like, it's either this way or this way. As long as you say it. Because the balls can either be together or not, correct. So, in this case, because this time the balls are distinguishable, but the boxes aren't, then the fact that there are n boxes doesn't really matter, right? Because you know a whole bunch of them are going to be empty anyway. So the question is just whether or not how the balls are distributed amongst each other. And you can either put one. You can either separate the 2, right? You can put 1 in one. You can put 1 in some box A, 1 in like some A, and 2 in some box B, and that's one way to do it. And note that it doesn't matter what these 2 boxes are, what the A, B boxes are, because it doesn't matter because they're indistinguishable. Or you put them together and you leave all the other ones empty, in which case it doesn't matter what this is either. And so these cover all possible distributions, leaving you with an answer of 2, correct? Part C. The balls are not distinguishable, but the boxes are. Charles. This one is arguably not an easy one. I will give you that, Charles. Oh, okay. Here we go. Numbers. So you have 2 cases. Either again. So yeah, you're separating them in the cases of being in the same box or not, which is absolutely a great idea. If they're all in the same box, then you have n because the boxes are distinguishable, right? So if you separate this in 2 cases, you either have same box, in which case there are n ways because you can pick which box, choose a box, right? And if they're separated, you're choosing 2 boxes in which the balls can go to. And if they're different boxes, right, you're choosing, you have n to choose 2 ways. Know that it's n choose 2 and not n. Know that order doesn't matter here. Order doesn't matter because the balls themselves are different. The balls themselves are indistinguishable, sorry. And because the balls are indistinguishable, you're basically choosing 2 boxes, as opposed to saying, I'm putting ball 1 in this box and ball 2 in that box. You're saying I'm choosing 2 boxes to put 1 ball each in. 1 ball in each. And this will give you n times n minus 1 over 2. This is choosing 2 boxes. And you add these together, right? Casework stuff, and you get n times n plus 1 over 2, which is the correct answer. Good work. And finally, part D. That's like now too close to part C. Aaron? Oh, why am I on line tool? The balls can be placed together or not, which means they're in different boxes, so that is 2 ways, correct. So this is the same as before, whereas in this case, it's just separate or together are the only 2 cases, as opposed to like being, oh, they could be this one. No, they're separate together, once again making the answer 2, Correct. Great. Good work, guys. So hopefully you guys understand, have a better appreciation for distinguishability. And you'll see how, and you might notice how it like relates to like whether order matters, and stuff like that. So that's fantastic. You guys get a very confusing. You get a very deserved break. Howard, I don't know if you can tell if you're. I can't tell. Yeah, this is like a bit confusing. Well, I mean, you all made it. I think you all made it in the end, which is great. But does everyone understand all the numbers, like all the answers we got? Did everyone say like, yes, I see we have those choices? Yeah, the formula part is it can get annoying, but it is how you should be. Like, this is like the sort of abstract thinking you should get used to in as you approach more difficult mathematics, let's say. Forget about that 10-minute break. Break until 5:09. By the way, before you go, I'm gonna stop recording. Can someone try to remind me to continue recording? All right, welcome back. Break is now over. So, slight change of plan. We will do our quiz on chapter 5 next week, and we will simply do chapter 6 today. So, luckily for you guys, that means there are no more problems for you to do on your own, because this one is going to try to help you get to think about these harder problems. Like I might ask you guys occasionally for ideas, but no one's gonna have to do problems on their own, except on the homework, in which case you'll have to do problems on your own. But so hopefully for this chapter, I didn't verify that everyone's back. Is everyone back? Hello, can I have verification that people are actually around? Hello, I've seen you. I see Howard and Rocky. Hello. Hello, Aaron. How are you today? Who else? We're still missing some people. Come on, people. Are you present? Hello, Ling. Hello, Nancy. Hello. Come on. I'm still looking. I'm still waiting on 3. Rin, Myron, Charles. I think, yeah. Rin, Myron, Charles. If you're there, please let me know you are around.
I am here.
Hello, Rin. I heard you. Hello, Charles. I see you. Hello, Myron. All right, Finesse, they're all here. So as I said, quiz on chapter 5 next week. Jump into chapter 6 for now. You guys don't have to do any more problems. Basically means I'm going to be speaking for the next hour about 7 fun and different problems. Not necessarily fun, but they are different. They're all like different caliber, and you guys feel free to contribute. Like, if you have any ideas, I'll help you take them. Because I think it's a good idea to think about it. But try to if I do a project, like, try to think about, how would you think about that yourself? Like, how would you come up with a solution yourself? And I'll guide. I won't be like, you just figure it out, I'll try to guide you, be like, okay, you might think about it this way, whatever. All right. So welcome to harder counting problems. So if you look at the chapter 6 in your book, you'll see 6.1 to 6.7, just chilling there. And we will be doing hopefully all 7 of them today. So let's get started. 6.1. A bowling tournament involves 8 participants who are ranked number 1 through number 8 before the tournament begins. The number 8 bowler plays a game head-to-head. What kind of tournament is this? Plays a game head-to-head against this number 7 player. The loser of this game comes in 8th place of the tournament. The winner bowls the game. The winner of that game bowls against a 6th player, and that loser is 7th place, etc., all the way until the winner of all of that plays against number 1 for the championship. Which means if you're ranked number 1, you have to win 1 game to get a championship, which is kind of stupid. And so, given that we know who these 8 people are, we want to figure out how many possible outcomes there are. We say an outcome is like, this person, this person gets ranked 1 overall, ranked 2 overall, etc., all the way to 8. So for 6.1, first of all, hopefully we realize the answer is not our normal 8 factorial, right? Like there's obviously some restriction on on the number. For example, like we know in 8, we know player number 8 and versus number 7, and loser goes to 8, right? Which means we already know like that we're restricted somehow. And so you might think, okay, how would I count this? You might think of like, oh, maybe it's like a factor of overcount. Oh, maybe if we overcount something. But it turns out that, and this is the first tip. This is the first I want to give you guys. If the question constructs its what's the more general word for it? Constructs its cases, go along with it. So what do I mean by if a question constructs its cases, go along with it? Well, what I mean is, in this question had a very sort of specific way of telling you exactly how placement is determined, right? It said, oh, the 8th bowler plays against the 7th bowler, and that's how you decide who's in 8th place. And then from there, you decide the 7th place, etc., etc., etc. And because of that, sometimes the best way is to just be like, okay, let me do that too. I will go through this. I will follow your procedure and see what I can do. So let's do that. Let's pit number 8 against number 7, okay? If we pit number 8 against number 7, how many outcomes can we get from this? Well, I mean, it's 2 outcomes, right? Either that number 8 guy wins or number 7 wins, and this dictates who's in 8th, right? Whoever losses win. And then the winner, right? It doesn't matter who. The winner between 8 and 7 is now up against number 6, right? And at this point, we're thinking, well, how many outcomes are there? There's 2, right? And again, take note that this is independence of number, because it doesn't matter who won the last game. It just matters that now it's that guy versus number 6, and leaving 2 outcomes, and this dictates 7. And we can keep doing this, right? Eventually going to the overall winner versus all of them, finally going against number 1, having another 2 outcomes. And this dictates both 2nd and 1st, right? And again, note that these are all independent of number, right? Like in every match, there are 2 outcomes. Either the guy coming up from the previous matches is winning, or the challenger per se, like the higher ranked one is going to win. And because of that, because these are all independent, we are just done. We just multiply all these 2's together, and we be careful how to count. We count the 2, right? 6, 5, 4, 3, 2, 1, 2, 3, 4, 5, 6, 7. There's 7 different 2's here, so the answer is going to be 2 to the 7 equals 128. So that makes sense. So the whole point, the whole point of this question, like what's meaningful here is that the question had a very specific way they constructed the possibilities for rankings, and sometimes it's best for you to go along with it, right? Instead of thinking like, oh, I'm going to look for overcounting, and and that's often that might not work if the way the question constructs the case is like complicated, like this question. By going along with it, it kind of tells you how to do it almost. Again, this won't always work. Sometimes it will ask you to be like creative and think outside its construction and think about what it really means. But oftentimes it will lead you to it will be at least a great starting point, and sometimes solve the question completely. But does that make sense? For each one of these questions, I want everyone to give like some sort of acknowledgement that they are okay with the solution. And at least grasp the main point of why this question is part of this list. So can everyone please, let's normalize this, guys. Let's normalize it to everyone has to like display something like in the participants list. So you can either display a yes, a thumbs up. Actually, do not use thumbs down. Do not say hi. So don't you like use the word, I want you guys to actually go in the participants list and like say something. Do you guys see me like with my thumb up in the participants thing? Thank you, Howard. Thank you. Everyone keep it up. I want everyone to keep it up. I'm not proceeding until I see everyone with it up. Does that make sense? And don't use like the negative one, like no, because then I'll assume that you didn't actually understand stuff. Great. I see a lot of them coming in right now. This is good. Excellent. We're saying Aaron and Rin. Rin, are you there? Oh, Aaron, thank you. I see you. Excellent. Rin, do you know how to Oh, fantastic. Oh. Rin's mic is now unmuted. Rin, do you know how to like do the thumbs up thing or the check mark thing?
Yeah, I do. I just usually don't do that. Like,
Okay,
I'm
well,
usually in front of my
I'm
computer.
normalizing it. I've decided I'm normalizing it to that. I'm sorry if this is like
Okay.
too much for if it's honestly too much for you, then you can perhaps not do it. But hopefully it's not that bad of a task. Okay, fantastic. All right, cool. So I'm going to expect this for every question. Fantastic. Moving on. A 6.2. How many triangles are in this figure? Oh boy, you know that's a. I'm not drawing. You guys see the diagram, right? I'm not drawing it. So you guys can put it down, by the way. You guys should probably put it down after every question. I've decided because that's a. I'm sorry, this is a lot of work for you guys. It's probably better than doing question, but please put it down after every question because I'm like asking you guys to read. Actually, I can force everyone to. I can force everyone to put it down. Fantastic. So 6.2, we want to find out how many triangles in figure 6.3. And unfortunately, I mean, we could count them maybe, but we might miss some, which is bad. So let's think about a smarter way. Like, how do we construct, like, sometimes obviously listing is not what this class is about. Sometimes it is, but not sometimes it isn't. So we want to think about smart ways. How do we construct triangles based on this diagram? Well, first of all, we notice that there aren't that many points to choose from, right? If we think about vertices, we kind of have the vertex on top, we have the vertex on the bottom, and then we have like a bunch of points where like the things intersect the middle line, right? And we see that, right? And furthermore, we realize that there's no line between, like there's no center line that connects the top and bottom, which means that we obviously know that those two can't be in a triangle together, right? And because these are all in one line, you can't form a triangle out of any three of them because that's not a triangle. That's a line. You know, that's what we call a degenerate triangle. Degenerate triangles are not allowed. Triangles not allowed. So because of that, that leads us to one conclusion, is that we either include the top one or the bottom one. What is a degenerate triangle? It's like if basically the 3 points are on one line and you try to form a triangle, you'll quickly realize that it's a line, and that's what we call a degenerate triangle. Is it the three vertices? Oftentimes we will not. This is not referred to as a triangle. It is explicitly said to be not a triangle. But to be like consistent within certain branches of mathematics, it can sometimes be regarded as a triangle. But for our sake, it's not a triangle. So we notice that we have to take either the top or the bottom one. So like that's like one thing. So that's like what we want to do. You want to think like, what do I have to do if I'm doing something? Like what's consistent? And what's consistent here is that either the top vertex or bottom, but not both, right? Not both are in the triangle, right? If we want to pick a triangle out. And right, this is the kind of like information you want to be deriving to help you narrow down what you need to do, right? And so with that, we might be able to do casework, right? Let's just case on the top. If we can just case on whether or not we choose the top or bottom. So if we case on top, we choose the top vertex first, okay? Then we need to choose two vertices from the line. And we can't just pick any two vertices from the line. We obviously have to pick, you know, the ones with lines going to them from the top vertex. And if you count, there are 7 lines. There are 7 lines here. Right, and I guess I'll do the bottom one too. There's 6 here. 1, 2, 3, 4, 5, 6. 6 lines. And so because of that, right, there are 7 vertices here, and that means that if we want to choose 2 vertices to complete our triangle, we of course have 7 choose 2 choices, which gets us nice 21 choices. And if we do the similar thing for the bottom, right, if we instead choose the bottom vertex as our first vertex, then we have 6 choose 2 ways from the 6 lines coming out of the bottom vertex equals 15 ways to do it. And these are, of course, destroy and exhaustive. And here we were very careful to make sure that they were destroying or exhaustive, right? This statement here, either the top or bottom, not both, are in the triangle, basically talks about exhaustiveness and disjointness in one go, right? You have to be one of them, but you can't be both of them. And that's what that is. So you can safely add this together to get your final answer of 36. Again, this one question not particularly bad, but hopefully you guys see its importance and like how this question was about deriving new information so you don't have to list them out, because listing them out is the most garbage way to solve something. and often will often make your answer wrong. So try to like figure out some interesting data. Try to figure out what are the key components of the question, right? Here, the top and the bottom vertex, key components of the question. And by singling them out, we were able to do it into manageable casework. All right, let's see some yeses and thumbs up if we're okay and satisfied with this question and its importance. Very nice. I'm seeing a lot of check marks. Not all check marks. I'm seeing some check marks. Excellent, excellent. See 5 check marks. I'm waiting on 3 people. If you need, by the way, this means that if you need to go, please let me know if you're like going to be away from your keyboard, because I will just be waiting on you to do something if you're not there. All right, everyone has responded affirmative. Everyone is okay with the question. Moving on then. Problem 6.3. Problem 6.3 states that we have a very interesting decimal. We have x equals 0.123456789, and then we just keep listing numbers. 10, 11, 12, 13, 14, and then all the way to 999. I should clear all. There we go. So we have this monstrous decimal, and we want to find out what the 2005th. Oh, gee, I wonder which year this question can be found in. The 2005th decimal or digit after the decimal. Okay. And so obviously we're not going to count 2005 digits. I mean, one of you can do that and spend the rest of your evening doing that. That's fine by me. But so we're gonna need to come up with a more clever way to come up with this. And well, how are we going to do this, right? We first realize, okay, well, if we're looking at the 2005th digit, we want a way to like jump. How are we gonna jump like these gaps? Because we're basically what you're doing is basically like, if you ignore the decimal, we're just listing out the numbers, and I'm trying to figure out what the 2005th digit I write here is as I keep going, you know. And so let's think about right, if we're able to pinpoint which number, right, like what number, like maybe I'm in the middle of writing the number, you know, 752, right? I'm like 75. Oh, this is the 2005th digit, right? If we can pinpoint which number I'm in the process of writing, that would help. So can we do something to find that? Like, can we divide by anything? No, it doesn't look like it. Like, it looks like, right? Oh, sometimes the numbers have 1 digit, sometimes they have 2 digits, and sometimes they have 3 digits. So we can't exactly divide by anything. But what we do notice is, well, first of all, there are not that many 1-digit numbers, right? 1 to 9, 1 to 9. There's 9. That is 9 1-digit numbers. That's not a lot. So, and I know we're gonna get past that. And after I write these numbers, I know I have written 9 digits, right? So I can just say, let's get past them, right? 9 digits. I've already wrote 9. And so how many more do I need to write? I'm still gonna need to write what, like 1,996. But at least we move past the 1-digit numbers, okay? And in fact, you could probably do this for the 2-digit numbers too, right? 10 to 99. Well, okay, first of all, how many numbers are between 10 and 99? If you respond, I really hope you don't get. I really hope you get this right. If whoever responds to this, how many numbers are there between 10 and 99? Let's see some numbers in the chat. How many? These are all the 2-digit numbers, correct? All right, fantastic, good work, Aaron. The answer is actually 90. There are 90 2-digit numbers here, right? 99 minus 10 plus 1. Learned that from week 1. But again, we realize that all these 2-digit numbers we also skip over, because right, what do we have? After writing these guys, we'll have written another 180 digits, and so after writing the 2-digit numbers, we'll have written 189 digits. And so at this point, all we have left are 3-digit numbers, right? We're going from we're now at the 100, right? Trying to write 100, and we're going to 999. So at this point, we still have 2005 minus 180 minus 9 equals how many digits is that? That I believe is I can't do math. I'm literally a math teacher and I can't do it. 1996. I believe it's 1816. Great. 1816. Okay. So we're looking at 1816 right now, and we're thinking, okay, well, so start writing 100, and I write 1816 digits, right? But at this point, we know that every number I write, I contribute 3 digits, right? So that means, why don't I just divide 1816 by 3 to see how many digits, how many numbers I'm going to write? And if we do that, right, we're going to get 605 remainder 1. And you'll see why remainder 1 is kind of nice to have. All right. So at this point, we know that we're going to write 605 numbers and then have 1 digit left that we can write. So if we're starting at 100, right? If 100 is the first number we're going to write, and we need to write 605 of these numbers, what is the last complete number we're going to finish writing? Right, so we know that because we know that we've cleared the 1 and 2 digit numbers, and we still have to write the 1816 more digits. But from this point on, every number we write has 3 digits. So we've chosen to divide by 3 to figure out how many numbers, how many numbers we need to write. And we've decided that it's 605 remainder 1, which means we're probably going to write 605 numbers. Right, we're going to write 605 of these 3 digit numbers and then stop, and we'll have 1 digit left. So which is the 605th 3 digit number that we will write? Does someone want to tell me? Not a trick question, by the way. I realize that looks like a 665. Oh, what am I undoing for? No, redo. Oh, it's too late. I have to redo everything. Does anyone want to contribute, or does no one know? 605th number. And the 605th 3 digit number. Okay, well, since no one wants to tell me, it's 704. And the reason, and the way we get 704 is because we realize, well, the difference between the number 100 and 1 here is 99, right? And if you realize, every time we think, okay, what's the next number? Well, we're increasing both the number we write and the ordinal number, the ordinal, like the cardinal number writing, like the second, it's the second number. We're also increasing that by 1. So this difference of 99 remains constant throughout us writing these digits, which means that this difference is going to be 99, and we simply add to get 704. Does that make sense to people? Cool. I will. Oh, Rin, people are saying stuff. Good. Okay, excellent. You don't have to do the thing right now. But this is a very, very important trick. Okay, if you want to, especially if you're thinking about what, if you're writing numbers in order and you're like, this is the first number right, the second number right, then this difference will be constant, and you need to keep that in mind. And if you sometimes forget, just try to write them out. Like, oh, I know the 100 is the first number. Oh, 101 is the second number. 102 is the third number. And you're like, oh, look, the difference. Look at that, it's 99. Pattern finding, But yes, once you decided that, but we're not done yet. Okay, so we know that at this point, I don't know why I just did that loop-de-loop there. I don't know what that was. At this point, I'll just go up here. At this point, we know that we've completely written 704, and we still have 1 digit left. That's what this remainder 1 means. We have 1 digit left. So we're going to start writing 705, except we don't actually write the O and the 5, because once we write the first digit 7, it's done. That's our digit. So we know the answer is 7. All right. Does that make sense, people? And it's okay if you have questions. These questions are getting harder. Like that is why they're presented in this order, I think. I would imagine they tried to make them go harder. If you have any questions, please do say so. Otherwise, I will wait for you all to say yes or thumbs up or any other positively connoted symbol. But does everyone see why the number we're going to try to write is going to be 705? But the 2005th digit is just going to the 7 bit. And hopefully everyone understands that. All right, I see a lot of people are good about it, and looks like more are coming. Fantastic. Good. Thank you. We await Howard. We await Howard's response. Howard, I swear I saw something there. I wasn't sure. I see it. Okay, fantastic. Everyone is happy with this question. Great. 6.4. 6.4. states that 9 parallel lines in a plane intersect a set of n parallel lines that go in another direction. So basically you have like, it's kind of like a waffle, right? Or whatever. It's basically got like 9 parallel lines going in one direction. You got n other parallel lines going in other directions. And so you can imagine it's kind of like a grid, right? If you try to imagine, it's like, oh, I've got these 9 parallel lines, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I've got the other like n of them coming in at some other angle. Those aren't parallel. You know, it's going to create this like nice grid. Of course, the grid size is going to depend on what n is, but that's the general gist of it. Hopefully, you guys see that grid in your mind. I will be erasing these. And we want to find out, and we know. Okay, so now we know that in this like grid, I guess in this grid we have a total of 360 constructible parallelograms. And so we're thinking, okay, 300. Oh, I should clear everyone. We have 360 parallelograms. So, and now we want to find n, basically. What is this number n, given that we know there's 360 parallelograms? And so this question is a little different, where usually the question might give us, you know, that it's not, it might give us n, right? It might be like 9 parallel lines intersect a set of 5 parallel lines. And how many parallelograms are there? But in this case, it's like, oh, we have n parallel lines, I'm going to tell you. So this question is testing if you're able to think about things more generally. Kind of like the problem we did earlier, 5.4.3. It was about thinking more generally and using and putting algebra in your stuff to get these like sort of expressions. So let's think about it, okay? So first of all, we're able to form 360 parallelograms. How do you even form a parallelogram, right? That's the question we're thinking about right now. How do you form a parallelogram? Because if we understood the process a bit better, I think we'd have an easier time, you know, solving this question. So how do we form a parallelogram? Does anyone have any ideas as to how we can form a parallelogram? Right. And again, when we're thinking about this kind of things, like how do we form something, we want to use what the question gives us. We can't like be like, oh, 4 points where are the points in this question, you know? So how do we form a parallelogram given the stuff that is given to us in the problem? Any ideas? Right. If we're able to put this into English, we can put it into math, and then when we put it into math, we can solve math. We know how to do that. 2 parallel lines. 2 pairs of parallel lines. Now we're talking. Okay, so how are we going to get these? Indeed, Charles is right. Parallelograms are formed by 2 pairs of parallel lines. Right? You got like you have the top and bottom, and you have the left and right. They're parallelograms. But where are we going to get these 2 pairs of parallel lines from? Right. So Charles is right when he says, well, we need 2 pairs of parallel lines. And the question now is, where are we going to get these parallel lines from? Well, we have some parallel lines, right? We got like the 9. We've got like 9. We got like 9 of them going this way. 9. I saw 9, but whatever. And we kind of got like some of them going this way. That's obviously not 4 is not obviously going to be n. I mean, it might be. And so we're making 2 pairs of parallel lines. So what are you saying? Are you saying I need to pick 2 from the 9 and 2 from the n? Is that what you're saying? That seems fitting, right? You know, 2 from the 9 and 2 from the n. And in fact, that is how you do this question. You're thinking, okay, I need to choose, you know, 2 from the n and 2 from the 9. And by doing that, we can think about this in our mind. Like let's just pick an arbitrary one. Let's say just pick this one and this one. Okay, great, whatever. And out of the n, I'm going to pick, you know, maybe this one and this one. Why not? And we see this, it does actually form a parallelogram, right? Right, we got this little parallelogram here. And here's the key about this, is that every parallelogram can be formed this way, and no parallelogram can be formed twice, right? This was the bijection thing I was talking about last class, where I was like, problems are equivalent, right? This is, well, again, we have this like sort of equivalence going on here again, where we're thinking, oh, I'm just choosing I'm choosing 2 from a committee of 9, and I'm choosing 2 from a committee of n, and I'm forming parallelograms with them, right? And again, we're making sure that there's actually like a 1-to-1 correspondence, where every parallelogram is formed by pairs of lines, but like you know, we're not overcounting or undercounting, right? We're not missing any parallelograms like this. Every parallelogram is formed by 2 parallel lines in this diagram, And we can't possibly count a parallelogram twice because the lines define where the parallelogram are. And so the key about this question is to first of all, think about how can I put it into math, right? And to do that, you want to think, given the information, like how do we use our existing information to find, to be able to express it mathematically? And here we know how to express these mathematically, right? How many ways are there to choose 2 lines from 9? Well, 9 choose 2, we have a notation for that. And how many ways are there to choose 2 from n? N choose 2. And these choices are independent, because it doesn't matter. Your choice of the 2 lines of the 9 doesn't matter, in fact. And this, as we discovered, is in bijection with the number of parallelograms. So we can say that 9 choose 2 times n choose 2 is 360. And of course, 9 choose 2 is 9 times 8 over 2 is 36. So we can get n choose 2 is 10. And now at this point, you might just, after doing this for some time, you might just recognize, oh, well, n is 5, great. But sometimes it'll be n choose 2 is something you don't recognize. And so it's at this point, it's at some of these instances where the algebraic form of the choose notation comes in great. That being said, you might not want to write n factorial over n minus 2 factorial. 2 factorial is 10. That's a bit overkill. Instead, what you can do is you can use the truncated version we talked about, which is list the first k numbers, which is 2 in this case, that go down from n and then divide it by 2 factorial, which is 2. And you can solve it algebraically like this. And you guys hopefully know how to solve this. It's a quadratic. Do people here know how to solve quadratics? Is this something we've learned? I know some of you do know how to do it. I don't know if all of you know. But the point is, sometimes solve some things algebra comes into into counting and probability. That's crazy. It's almost as if the math subjects are uniting together, But okay, does this make sense? Do we see how we got n equals 5? If we do, then please throw me some verification of some sort, and please leave it up as well. Thank you. Thank you. Looks like people are okay with it. Again, if you have any questions, please do let me know. You don't have to say it out to everyone. You can private message me. But I want to make sure everyone is okay with this problem before moving on. Come on, folks. I'm gonna need you 3, Myron, Nancy. Okay, thank you, Nancy. Thank you, Rocky. Hello, Myron. Are you with us today? Hello, Myron. I think I saw it. I wasn't sure. I might be going crazy. Myron, are you there? How do I ping someone? Ping. No, I can't. I can't actually do that. Oh, Myron is here. Fantastic. Great. Okay. Cool. Everyone seems okay with it. 6.5. We're almost there, guys. 3 more problems. 6.5. Jamie is a house painter. She has been given a contract to paint any K of the houses that she wants on a street that contains N houses. Janie has J different colors of paint in unlimited supply. She can only use one color on any given house, but for each house, she gets to pick which color to use. In terms of J, K, and N, in how many ways can Jamie fulfill her contract? Okay. So this question's like kind of like a toss-up, right? Some people see this question and instantly know the answer, even if they are not very familiar with counting. And some people who are very familiar with counting struggle a little with this question, which I really don't understand how. Because this question, it's just I don't know why so many people I don't know why this discrepancy is so big in this problem, but we'll see. So I think the key in this question is to think, okay, we have all these variables. We're just given 3 variables, right? Out of N houses, right, we need to paint K of them. And for the K of them, each painted with one of J colors. And there's a lot going on, right? This is not there's no explicit formula that we know yet. That will do this for us. Well, because that's the point of the question. We want to do it first. So we might think so this might be overwhelming at first, but you want to think about this human-like, right? So this is a new tip. Think rationally and humanely. Okay, I'm going to call it humanely. And what I mean by that, well, Jamie here is a house painter. So if you were Jamie, what would you do? Oh, Janie, sorry, not Jamie. So if you were Janie, what would you do? If you had to be like, okay, I gotta paint these K houses and each of them's gotta be J colors. What are you gonna do first? What are you gonna do? What's the first logical step to do? What's the first logical step to do? What do you think? It doesn't matter. Just let me hear your ideas. What kind of ideas do you guys have? If you had the choice to paint any K of N houses, each a color out of your J colors you have, what's the first thing you're gonna think about? Because there's obviously this feels like a multi-step process, So what are you gonna do first? Let's see. Let's open it up to the floor. What are we gonna do? Does no one have any ideas as to what they would do in this situation? Okay, that's fine. Well, I think if I were Janie, I'd probably pick the houses first, right? Like I'm out here trying to think. Okay, well, I'm gonna paint these. Well, I want to know what houses I'm painting first, right? Maybe if I look at the house, I'm like, oh, this house would look really good in blue. Probably not, but I mean, obviously that's a joke. But the point of this problem is to think, how would you do? How would you choose, right? And that's the real beauty, and that's a real idea of counting. Is when you're counting something, you're basically thinking, how many ways can I construct or do something, right? And your thought and the decision process you make, or that you're supposed to make in that situation, should be the decision process you do to figure out how many ways there are in the first place. And so the first thing you should do is pick the houses. Out of N houses, you want to pick K of them. Order does not matter here because you're going to paint the K of them anyway. So you have N to the K. Great. And now that you've picked your houses, we need to color each of the houses, right? Let's say we color house 1. How many ways are there to color house 1? Well, there are J ways because there's J colors. And how many ways are there to color house 2? There's also J ways. How about house 3? Oh, J ways, crazy. All the way to the Kate house that you picked, J ways. And to overall, of course, it's all independent. Keep that in mind. This gives you J to the K different possibilities. And these two choices are also independent of number, right? Because it doesn't matter which K houses you pick, you'll have to do this process every time. Hence making the overall answer N choose K times J to the K. Does that make sense? Charles says yes. Thank you, Charles. Very cool. And Rocky also says yes. Thank you. Very cool. And for a question like this, if you're not sure where to start, perhaps Rocky, don't lower your thing. I want to make sure everyone says it. Everyone, I want to make sure everyone has their stuff up. This is by the way, guys, I'm verifying if you guys are here, or if you guys are understanding. Please announce that you are okay with this problem. For this kind of problem, I think what you should if something, because obviously this might have been a simpler, quote unquote simpler example. It can get pretty complicated. Try small values. What if J was 1 here? Basically, the question would be, out of N houses, we need to paint K of them. We need to choose one of one. Well, no, you don't have a choice for color then. You're just choosing the houses. So at that point, it'd just be N choose K, which is what you'd expect based on our formula. So sometimes you might want to substitute some values in, not to one, maybe get you on the right track, and 2, help you verify your answer if you get one, right? If by plugging variable in, you're like, oh yes, this makes sense. Good. Myron and Rin, I still haven't seen your little check marks or whatever yet. So that is okay. Thank you, Myron. Rin, hello. Are you there? I know this might seem stupid, but I really want to make sure everyone understands all these strategies because I'm basically throwing you into challenge problems for the homework because there are no review problems for chapter 6. So I hope you guys are ready to apply this stuff, or use your brain, be creative with stuff. Cool. 6.6. We still have we have 12 minutes. I think we can do it. So 6.6 is a grid. And we want to find how many paths are there from A to B, going from right or, oh, this sounds familiar. We got it. Oh, and you look at the grid and it's like all messed up. So basically, our grid is not looking good because we are missing a lot of lines. And as you guys can guess, you cannot go on lines that are missing. So I'm just gonna draw the thing first. Right. And so first of all, right, we remember how we did it for when they were all filled in, right? We did like a little argument about how it was the same as a choosing committee, and that was all great. But now I don't know if we can do something like that because it seems almost at random, right? And that's never a good thing in counting. If things are missing at random, that's not. There's one missing here. We have a white line. There we go. High IQ. Like that should do it. Okay. We have this line, and we have this line. Oh no, and we have this line. We have this line, this line. We got this line. Okay, so the question is, how many ways are there to get from A to B? Given that we can only move right and up, and we have a lot of patches, and so you might think, oh, there's a line here too. Oops. Great. So there's obviously probably not going to be a formula for this, right? If you guys, hopefully you guys recognize that if something as random as this probably does not have a formula, because if it did, that'd be, boy, I mean, there might be, but it's not going to be a pretty formula. So it's up to us to be like, to actually count them. But we don't obviously want to just count the number of paths because that's not great. So instead, let's think about simpler problems, okay? And so the key to this question is to think simply. I feel like isn't that like the slogan of some like juice company? Whatever. Anyway, think simply. And so how do we think simply? Well, we can make the question easier for ourselves per se. And right, and sometimes bringing questions down to simpler versions can help. So, okay, well, let's think about this. How many ways are there to get from B to B? Yeah, I know I just asked that. How many ways are there to get from B to B? Not a trick question. How many ways are there to get from B to B? Please, someone let me know. Does anyone want to contribute as to how many ways they think there are to get from point B to point B? Please note that I did say point B twice there. 1, correct, Charles. There's one way to get from point B to point B. It is to do nothing. Correct. Excellent work, Charles. Keep it up. But you might realize also that, well, if I'm on this point, for example, I don't have a lot of choices. I have to go up because, again, you can only go right and up in our question. So maybe label that 1 too. In fact, everything on this side is probably 1, right? If I start at any of these points, I'm forced to way up. And the same probably applies if I'm forced this way too. If I'm forced to go right, if I'm on this side here, I'm forced to go right the entire time. So these all have 1 way. Great. I'm feeling good about myself now. Okay, well, let's spice it up a little. How about this point here? Well, how many ways are there to get from that point to B? And does anyone want to tell me? It's not, again, not a trick question. Please, this is the point of this is not a trick question. Anyone want to let me know as to how many ways they think there are to get from that point to B? From this point, sorry, I'll circle it. I drew a new point in.
3. Wait, yeah.
Charles
2.
says 2, Rin says 3. I see the conflicting answers.
2.
You can go around, right?
Around.
Wait, which
Seen
ways
around.
can we go?
Like you
can
could
go
go
right and
down.
up. Make sure you read the question. You guys are reading these questions, right? I'm not like just drawing grids on the graph and like asking you guys to do things. You can only go right and up in this question.
Okay.
But yes, the answer is 2. You can either go right and then up and then right. There's no other
I
ways to go
forgot
around.
to subtract one.
So the answer is the answer is 2. Great. Let's put that down. Great. And we could start doing this for like all sorts of points, right? At this point, again, you can think of this as a smaller grid. You might think, oh yeah, 3 choose 2. Great. 3. And at this point, you'll think, 4 choose 3, 4. Sure. That's like whatever. But at some point, you might at some point it'll get pretty hard. Like, how about here? Like, what about this point? I've just put a point in, and I'm like currently I've circled it again, by the way. How many ways can we get from that point to B? Does anyone have any ideas? One. And why do you say 1, Charles? Because you can't go right. From this point, first of all, from this point, you have to go up, right? You can't go right. And you're not allowed to go down left. So you're forced to go up. And from then, you know that there's actually one way to get from this point to B. And so you know there's one way. And so this inspires us a little, hopefully, is to think, well, once I get to a point, like once I get a point to I already know, like if I'm moving along, I get to this point, then I know from, like let's say I make a path from A, right? And I'm moving along, and I go, da, 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 da. Once I get here, I know there's only one way to go because it says here 1. Look, it says there's only one way, right? And so let's use that to our advantage and come up with a way to feasibly do this process. And so the final question I'm going to ask you guys is this point. Knowing what I've said, knowing what I just said about like this double checking thing, how many ways is there to get from this point to B only going right and up? I'm going to draw a nice big white rectangle on this one because there is not, it's not here, guys. That line's not here. Okay. How many ways? What do people think? I'm going to fill these points in. It's bothering me how unfilled they are. Four? Oh, yes, that's correct, Rocky. And why do you think 4? Did you count them? You might have counted them. That's probably fine. You got counted. Great. Well, you'd be right. You counted them right. 4. But Rocky, I'm going to ask you a question. Out of the 4 ways you counted, how many started by going up? Like out of the 4 ways you counted, right? You counted 4 ways. I don't know if you remember them. How many ways start? 1. Okay, interesting. And how many? And that means you have 3 going right. Ooh, interesting. You said 1 started by going up, and then you said what? 3 started by going right. Interesting. Yeppers indeed. So hopefully that has inspired. Hopefully you guys have noticed something. Basically, if I go in a direction, I have dictated myself to how many paths there are to go from that point to B, right? For example, if I go from this point, right? If I start by going right, I already know I only have 4 ways to go from there, right? To get to B, because it says there 4. And similarly, if I go up, I'll also only have 4 ways, which means I can just add the 2 numbers together, 8. Wow, that was quick, right? I didn't have to count anything. And so that is the key bit about this problem, is that this is how you're going to solve the problem. You're just going to go through the entire grid and start plugging and chugging numbers. This is a lot of fun, by the way, and very satisfying when you get to the end. And so you start doing this, right? At this point, you look at the one up and to the right, and you're looking 1 + 1, 2. Great. This point, I'm looking up and to the right, 3. This point, I'm looking up and to the right, 4. This point, I can't exactly do yet, so I'm going to ignore that for now. This point, I can't go up. I can only go right, so it's 4, right? And again, we remember this from our original example where we're forced to go in and we just copied the value. And we have this point here, which is going to be 7, right? Because we have the 3 + 4. I'll label this point as well. It's not important, but I'll label it. Here, we're going to have 7 ways because we are forced to go up. Here, we're going to have 11 ways because we have the 4 up and 7. And finally, at this point, the A we want, we're going to have 11 plus 7 is 18 different ways to get from A to B. And we are done. And so another thing, the other strategy here is to find a recurring pattern sometimes. Sometimes in like a question like this, you want to like think simply into finding a recurring pattern. If you think simply, you might be able to you might be able to like see a pattern, and then you want to like think to yourself, does that pattern work? And if it does, exploit it until you get the answer. So let's see some yeses. Let's see some yeses, I agree, or questions in the chat for this problem. Thank you, Myron. Myron is okay with this problem. Charles and Howard. The system, guys, the system. Use the system above. I see your things, but use the system. Put the check mark. Put the check mark. Let me see some check marks. Yes, good check marks. Okay. Come on, Howard. I know you've already said it, but I want to see the check mark. Thank you, Howard. Howard, thank you. And now I think we're missing Ling. Hello, Ling. Do you agree? Do you agree with the solution, or are you not there? Or both? Yeah, just, no. Yeah, this is good. This is good. I feel I have so much power when I just see an entire participants list of check marks. Excellent. Okay, good. A lag, fair enough. All right, we have 1 minute left. And unfortunately, 6.7 is an extremely long problem. But the general point of 6.7 is once again to think simply. Because okay, I'll read poem 6.7. Spiffy the spider has 8 legs. Yes, it's a spider. Each of which is a different color. Spiffy has a sock and a why are his legs different colors? Spiffy has a sock and a shoe for each of his 8 legs, so that he has 1 sock and 1 shoe on each of the 8 colors. And how many ways can Spiffy put on his socks and shoes if each sock and shoe must go on the leg with the matching color, and the sock must go on before the shoe on each leg? Okay, so there's a lot of stuff going on in this question. First of all, note that the shoes and socks in this question are indistinguishable, okay? Right? It does not matter which shoe I put on which, it does not matter which shoe or which sock I choose to put on. The point is I put a sock or I put a shoe on the leg. Now the legs, of course, are distinguishable. They're different colors. See, and so this is the kind of indicator I was talking about, where you want to think, okay, like, and again, being able to say these things is very important. Be like, yes, I realize that, like, being able to immediately recognize distinguishable, indistinguishable, very important for solving a question. But once you do that, now you're thinking, okay, well, how am I going to do this? Because first of all, the restraint here is, the hard part about this is that you have to you're putting on 16 things overall, right? You're putting on 16 things, right? And 8 of them are socks and 8 of them are shoes, but you have to put the sock on first. Sock before shoe for each leg, right? And so, okay, this is gonna be this feels pretty hard, you know? And unfortunately, if you're not extremely good at problem solving, you will not immediately see that this is a question of just overcounting by a factor of 500 of like 256, which is what it is actually. So unfortunately, I don't think you guys will see that immediately, because that is, why would you see that? But perhaps it might help to think, okay, bring it down simpler. What if this guy wasn't what if it wasn't Spiffy the spider, but it was Sally the human? Okay, if it was Sally the human, all of a sudden we have 4 shoes. Oh, 4 shoes. 2 shoes and 2 socks. All right, we're not going to talk about Sally the human. So this is us making the question simpler. Sally the human, okay, has two legs, by the way, in case that wasn't obvious, and thus needs to put on 2 socks and 2 shoes. Right. And so first of all, we're basically arranging these 4 things. So initially we're going to have 4 factorial equals 24 ways to arrange them, right? To arrange. And in fact, we could probably list them all out. Now, I don't want to list them all out. So can you please flip to chapter 107, please? to look at this very, very unnecessarily detailed table of ways for Sally to dress her feet, I guess. Wow, I don't know. I don't even want to know how they got this like sock and shoe font. Like, is it like a part of a font? That's crazy. But anyway, are we all on? We're all on page 107. Yes. Page one. I'll write that. Page 107. Please go to page 107. So you'll see that those 24. You'll see those 20. Those are all 24 different ways to dress her for her to dress herself. And at this point, if we don't understand like how we can like think, oh, sock before shoe, like how do we arrange that? Well, we can just try to cross them out. And so that brings us to my final technique, which is listing simple methods. Sometimes listing will help you understand the question. So basically, this goes in tandem with making the question simpler. If you bring down the numbers in the question, in this case I brought the legs from 8 to 2, then listing becomes feasible, right? Like I could probably list all 24 of these if I had time. And then by literally just simply looking, okay, which ones of these have illegal sock shoe replacements, right? Oh, this example puts on the right shoe before the right sock. That's illegal. You can't do that. And by doing that, you'll be able to count them, and hopefully that will inspire you to find a pattern. That'll be like, oh, I see it was exactly half now. That's interesting. Why is it exactly half? Does that apply to the previous question? And we see here, for example, if the next table, so like you saw the first table there, the second table on page 107 is the number of ways to salad dress only if we consider left foot restrictions. So only restriction here is that the left sock must come before the left foot. And they cross out actually exactly half of them, right? Out of the 24, only 12 of them are around. So we keep that in mind, right? And okay, now if we flip to page 108, we have a third table. And now this table builds off of the second table and now also adds the right foot restriction, therefore representing both restrictions. And out of the 12 left, another half was whittled down to 6. And so now we're thinking, okay, every leg or foot or whatever, we reduced it down by half. Can we apply that to a more general setting? And the answer is yes. And so once we realize, okay, so this is like the key part. When you do the listing, you're like, okay, so now you're thinking, is it half? Is it halved per leg? That's a very weird question out of context, by the way. Is it halved per leg? And like we can now think about that means we're basically thinking it's overcounting by 2. How are we overcounting by 2? Let's say, and the answer is, well, because let's think about an arbitrary arrangement. Okay, so for some leg, we're gonna call the shoe. We're gonna say it's the shoe S, right? It has shoe S and it has sock. Oh, they're both S. No. Basically, let's say for some leg, right? Because the legs are distinguishable, and like let's say we're putting on the put on sock. We have the actions put on sock and put on shoe, right? On this specific leg. And so these are 2 actions that will appear in our chain of 16, right? Because we have 16 different actions we can do. And we have to do all of them at some point. And we realize that put on sock and put on shoe, this specific one, with I'll put a nice little star next to it, represents the leg we're considering, right? So let's say we have a specific arrangement, and let's just say, I'll use a different color, use a blue star here. Let's say that our 2 appear here, right? This is a legit, like this first of all, this is a good, according to this sum leg, this is a good arrangement, right? I have put on the sock before the shoe for that leg. However, if we were to switch these 2 around, right? If I switch these 2 around, I would have a not good. This is a not good. I'm not allowed to have this, right? I am putting on the respective shoe before the respective sock, right? I'm putting the shoe on like the 5th thing I do, and the sock's gonna be like the 11th thing I do, and that's not good. So what do we realize here? Well, for the rest of the 14 slots, right? Where were these 14 slots? These did not change, right? And in fact, if we think about it, that means regardless of what, and of course the positions here didn't matter, which means hopefully you guys see that for every valid thing for this leg, there's a respective invalid one, right? If I simply switch the positions of the sock, putting on that sock and shoe, I have exactly one good arrangement and one bad arrangement. And using that logic, I realized then that exactly half of them are going to be good and half of them are not going to be good. Does that make sense? Right, and so this is us using our inspiration here, being from using the simple ways by looking at Sally the human. We're thinking, okay, maybe it's half, and we're trying to justify why is it half, and this is what we come up with. And once you realize that, then you realize, okay, well, there's 8 legs, right? And if I can do this for every leg, right? Because why can't I do it? Because putting on the sock and the shoe on the next leg are 2 separate, like they're completely independent from blue star and orange star here, right? And because of that, they're like kind of part of this rest of the 14, and it's almost as if the sock and the shoe, like this sock and this shoe, doesn't even exist, right? And it's still the half thing. And so for every leg we're doing, we're going to reduce it down by half. So that means that we are overcounting by a factor of 2 to the 8th equals 256. And of course, now I'm thinking, well, what are we counting in the first place? And the answer is the number of arrangements. And hopefully you guys know the number of arrangements. It's 16 factorial, right? There are 16 things. I'm just arranging 16 things without restriction. But we have decided that we're dividing by 256 here. And apparently that number is 81,729,648,000. Not that I would expect you to write that. But are we clear on how on this? Of course, the number is not the important part. The way we got the answer is of course the important part here. Sally the human, we use it by listing. That's right. Listing is now a good strategy, guys. Listing is now an endorsed strategy in this class. Listing for simpler cases is one of the best ways to see a pattern when you don't know. When you like, because like obviously ideally you'd be like, oh, yes, I realize that it's an overcounting by half, but sometimes you won't. We're not all going to get, you're not just gonna magically like figure it out for every question. So sometimes you should try listing it out to get like an idea of what it should be. In this question, it was pretty obvious. Like half was removed and then another half was removed, and so you're probably thinking, oh, you just removed half, and then you want to think about it in your head and be like, okay, why does that work? And then you come up with an explanation. And you convince yourself and you convince your readers if it's like a please show your work, and then you get your answer, which is great. But does that make sense? So hopefully, I want to see some yeses. I want to see some yeses in the chat. I want to see some yes, not in the chat, in the participants list. I want to see some people with a nice little green check mark next to their name. Come on, let's see it. Are we okay with this question? This question is by far the weirder one of the bunch, but it is a fantastic question, I think. Come on, I want to see some more check marks. All right, while waiting for these check marks, hopefully these 7 questions made some sense. Again, these are what we call the harder problems, right? This is where you have to use what you've learned in like not just normal ways, because we learned each of these methods as a way to solve a specific type of problem. If you remember, we learned combinations to solve specifically committee problems. The addition, when you add and multiply, those are because of simple caseworks and or independence of stuff, right? Sometimes you just had this question, which is not related to anything. And it turns out sometimes your combinations don't refer to committees; they refer to parallel lines. And so it was about going beyond like the normal stuff, and then being able to think creatively and simply, I guess, and think logically as to how and it goes back to the fundamentals. Like, why do we add here? Why did we multiply? Why is this a combination? These are what these harder problems oftentimes test you on. So with that in mind, that will conclude today's class. Aaron has still not said yes, but I will assume I will assume that he is okay with these problems. I will stop the recording